Very recently, I got to know about Llama 2. It is an open source pre trained large language model created by Meta team. It can be used to solve several different use cases, including creating a chatbot. So I went to Hugging Face, downloaded the bot, added it in my app, and created a very simple chatbot where you can ask questions. That question will be pinged to Llama 2 model. Llama 2 model would respond to the question, and we are going to just display the response. I asked a question: write a random story which is not there on internet in around 100 words, and assumed that model will take roughly 5 to 10 seconds to reply. I waited, and after a solid 2 minutes, I got a response. At first, I thought there must be some problem with my code. I googled and found that problem is not there in code. It is in the server where I have deployed this app. That server was purely CPU based server, and I have to use GPU to speed up the inference process of the model so that model can respond quickly. Searched and found that NVIDIA T4 is a GPU which we can use. I went to AWS and bought a G4X server that has NVIDIA T4. I deployed the app there. I came back, asked the question again, and I got the response from model in less than 5 seconds. That got me thinking, what is the difference between a GPU and CPU? Why is GPU this fast? And if GPU is this powerful, why cannot we just replace all of the CPUs with GPUs? GPUs, or graphics processing units, were originally developed for rendering graphics and accelerating image processing tasks. GPUs were designed to handle the complex calculation involved in rendering graphics for video games and simulations. So, in a game, all the objects that you see is represented in the form of numbers in a matrix. Every object will have a coordinate of where it is kept, a thickness, a color attached to it. These properties of the object is kept in a matrix. And as you see some action movement in the video, your video game, there's tons of matrix based calculation happening. And the role of GPU is to speed up all of this matrix calculation. How does GPU helps in parallel computing? Let's say we have a huge task and it is core that can process and complete the task. So in this case, when we just have one core, we'll grab the whole task, assign it to that core, and wait for that core to complete the task. But what if instead of one core, we have four cores? Instead of just assigning the whole task to one core, will it not be better if we divide the whole task into subtasks and then assign all of the subtasks to a separate core? And then all the cores can parallelly process their subtasks and get the job done in 1/4 of the time. So, from this, we know that the more core you have, the more you can process in less time. And if we compare CPU with GPU, CPU will generally have 2, 4, 8, or 16 cores. GPU can have from 100 to potentially thousands of cores. So we can see that okay, there's core that is making the difference, but the way tasks are assigned to these cores create a big difference as well. Let's see how that works. So we have a scheduler. When scheduler receives any instruction, it would then reassign that instruction to a thread and ask that thread to complete or process that instruction. This thread in turn will take help from a core that is called CUDA core for mathematical calculations. The idea behind CUDA core is quite simple. You have an instruction, that instruction needs to be processed. You push the instruction to the CUDA core. First, instruction will get to dispatch unit. Dispatch unit then assigns that instruction to either floating point unit or integer unit for its processing. The output lands on result queue, which can then be pushed ahead. So till now we had a scheduler, a thread, and a CUDA core. Let's make one small change to this setup. A scheduler, instead of assigning the instruction to one thread, it assigns instruction to one warp, and one warp has 32 threads. So same instruction is assigned to 32 threads, and all of those 32 threads can work with their CUDA cores to process the instruction. The only difference in these 32 threads would be the data they are processing will be different each time, and that is why it is called single instruction, multiple data. So when you have bulk of data, you have same instruction, you assign that instruction to the warp, and warp will then assign same instruction with different data to all of these 32 threads, and it will get processed. So this scheduler strategy does help a lot in parallel computing as well. Now that we know why GPUs are good at parallel computing, let's understand how machine learning fits the use case of GPU. Although machine learning neural network looks complicated, but under the hood, there's just a lot of layer after layer basic algebra equations and matrix multiplications. So if you are at layer 1, the first layer, you already know all the inputs and the weights, and you just have to multiply the input with weights, right? So instead of doing it sequentially, one node after the other, we can just parallelly process all the nodes on the same layer. Okay, so till now, we know that GPU is really doing well. We still have one question with us. Should, if GPU is that good, should it not just replace CPU? And to answer that question, let's solve this simple problem. We have to multiply these three numbers. We ask GPU to do it, and we ask CPU to do it. What do you think? Which one is going to answer this faster? And the answer is CPU. In simple calculations, or when you do not need loads of parallel computing, when you do not have a lot of data to parallelly process, generally the complete scheduling and assigning all those threads and the complete architecture that makes GPU better for parallel processing makes it slower and not very useful for small calculations or processing sequential or simple things. Although fundamentally the core idea of both CPU and GPU is built upon fetch, decode, execute, write back. That is, you fetch the instruction from the memory, you decode it into a format that your ALU can understand. ALU is going to process it after getting the instruction from scheduler. After processing, it is going to write back to the memory. But the use case that CPU is trying to solve is completely different from that of a GPU. The way CPU architecture is developed, the way CPU architecture is designed, each core can run broad variety of instructions, one after the other, coming from different processes that are context switching. And the focus is on how to process these individual instructions efficiently. And that's why it is called general purpose computing. You can run all different types of softwares on your laptop like Word, Notepad, Excel, browser, all of it is running on CPU. while GPU is a specialist processor. It does not focus on performance of individual instruction. It focuses on bulk throughput. So if we take the example of three numbers which we were multiplying, three numbers, just multiplying three numbers, you know that CPU would do it better than GPU. But if you try to multiply millions of numbers, a GPU will outperform a CPU. Now, how do you use GPUs? There are three layers involved. The top layer is your application and the framework which you are using, that can be PyTorch or TensorFlow. The bottom layer, that is the hardware, the actual GPUs. And for your app to use GPUs, it has to go through CUDA library. If let's say in your application you want to load one of the AI models and do all of the inference on GPU, you have to tell CUDA that this is the model, this is my input, and I would like to use GPU. And then CUDA will enable our app to consume GPU hardware. Setting up a GPU server is quite easy. All you need to do is to install the NVIDIA driver so that your operating system can communicate with the GPU, and then you can install the CUDA library. For that, you can visit the NVIDIA website, select your operating system, the version, and you will get the complete installation instruction there itself. Once your GPU server setup is complete, you can validate that by writing a small code. You import torch library. You can check whether CUDA is available and what is the GPU device which our code will be using. So in this way, we top layer, app framework layer, can check if we have access to the hardware layer, that is the bottom layer. To use CUDA, you specify the device. So CUDA 0 means we would like to use CUDA with device ID of 0, the first GPU. And then we load the tokenizer and the model, and then we push the input, the text, to the tokenizer and ask it to load the output, the tokens, on the GPU side. That's why there is a .2 device. And then we tell the model to load on GPU side, and the complete inference of the model will be done on the GPU side. Now, if we had not loaded the model and the input on the GPU side, the complete inference would have happened on CPU side. Now, instead of writing all of this code, we have got few wrapper libraries. Hugging Face Transformers library that has pipeline API, with which you can do all of this, loading the model and moving it to GPU in single line. You specify the model, you specify the device, and internally it is going to take care of it. The only problem with this approach is we are specifying the device ID, or exactly which GPU we would like to use for inference. What if our model is too large for single GPU? What if we want to load partially a part of model on first GPU and the other part on the other GPU? And for this, we have a library Accelerate created by Hugging Face team, with which instead of specifying the device ID, you can just say device underscore map auto, and it is going to check the size of the model, how much it can load on GPU, how many GPUs it would need, or partially load it on CPU and partially on GPU. All of it is going to take care of by itself. This is how you use GPUs for your model. Quite simple. Thank you.